Hi everyone. In this presentation, we will talk about sodium-cooled fast reactor with MOX fuel, like the Finnish French reactor. My name is Sebastien Andrea. I'm the third year PhD student working at the French Alternative and Atomic Energy Commission, and I also work in collaboration with the Laboratory of the Mechanic and Acoustic. In this presentation, we will talk about my PhD work that focus on multiphysics modeling of fluid cladding interface in sodium fast reactor during loss of flow transient scenario. A loss of flow transient scenario is triggered by a loss of primary pump, which induce a transient regime between forced and natural convection. After the loss of the primary pump, the reactor search to reach the thermal equilibrium governed mainly by neutronid feedbacks, particularly the Doppler effect and the fuel column dilatation. On the other hand, we know also that at the interface, the thermal exchange coefficient influence the Doppler effect and the mechanical interaction influence the fuel column dilatation. That's why my PhD work is focused on fuel cladding interface. During irradiation, power cycles induce cycles of opening and closing of an initial mounting gap between pellet and cladding. In this work, we have brought to light that after a certain period of time, a bonding phenomenon can be observed at the interface. We made the assumption that this bonding is a chemical bonding created by diffusive reactive processes. And we also consider that during power cycles, depending bonding intensity um, and power decrease, the bonding can break or can oppose the thermal shrinkage in opening the gap.
Now we have described the problem to model. Let me show you the multiphysics model developed with the help of the Laboratory of Mechanics and Acoustics.
To model pellet cladding interaction, we have developed a multiphysics contact model with a full coupling between thermal, mechanical, and chemical aspects of interface. To describe bonding evolution at the interface, we have introduced two variables. The variable C that model bonding intensity evolution enhanced by chemical reaction, and the variable D that model damage intensity enhanced by creation of material defects. In equation 1, we can see the opposite of bonding to thermal shrinkage is modeled with an interface rigidity depending on the variable C and D. In equation 2, we can see that bonding intensity evolved when a thermal threshold is reached and when the chemical energy brought to the interface is higher than the mechanical energy induced by loadings. And finally, the damage intensity evolved when the mechanical energy induced by loading is higher than a threshold called the critical fracture energy.
Let's go with me to apply the previous model developed on sodium cooled fast reactor modeling and simulation.
If we look at the interface behavior under power cycles, we can observe that the model developed calculates the normal displacement jump or tangential displacement jump and the thermal flux at the interface. And as we saw earlier, those influence neutronid feedbacks and thus loss of flow transient. Simulation are at few pin scale are in progress, and the outlook of this work is to integrate this model developed in germinal fuel code and simulate loss of flow transient. Thanks for your attention.